So I couldn't just arbitrarily throw out.
So let's work through that. So we could say sulfuric acid, and in this case, it might be sulfuric acid. I don't think it's sulfuric acid.
Strong acid, right?
No, because your pH is still pretty high if you look at those equivalence points. So you look at the pKa for sulfuric acid, its first acid equivalence is at pH negative 7.
Oh.
Yeah, it's really acidic. So if we're even on the curve, we're not looking at sulfuric acid.
Yeah, I see.
So where are you pulling those numbers from? How do you know that?
I've had it memorized.
So it's just you memorize the equivalency point of certain acids, that's how you
The
know.
pKa of certain acids, and we'll talk about what the equivalence points mean. But the pKa for some things I've got memorized. And I was told when I went through chemistry, these are pKa's you should memorize. I never did. But I've worked with enough of them enough that I've started to have them kind of internalized. So the first thing we want to start with is exactly where you started your first statement, Mike, diprotic acid. Okay, how do you know it's a well, what would a diprotic acid look like? So what would a general formula be? So now we want to start to build out an equation. Once we have an equation, we can start to overlay things on our curve. So what would a good formula be for a diprotic acid?
Like an example, like H2SO4.
Okay, H2SO4, so we need the H2, that's our diprotic part. Okay, the SO4 is getting too specific though. That now says it's sulfuric acid. I don't want to get that specific. I want some general term I could drop in there. So, A. Keep it simple. Okay.
So why is it called a diprotic acid?
So
Because
diprotic, it has two acidic hydrogens. And they have to be acidic hydrogens, because there's other cases where you'll have hydrogens that aren't particularly acidic. They wouldn't count to it being a diprotic acid.
Okay. And you know that because there's two equivalency points, not because of the buffer?
So how did you know that, Mike?
Well, multiple equivalence points would be a good indicator.
So what you're looking at is your equivalence point. Okay. So those red dots, this thing is going to get really, really full of information. So I'm going to try and key this. So these are our equivalence points. And we're going to add some information about what happens at the equivalence point here in a second. So before we even get to that, though, now that we know we're looking at H2A, well, how do you know it was an acid, actually? Sorry.
Because it begins with a very low pH.
If we look at our initial point where we're starting the whole process off, we're starting at a low pH, it's an acid. Okay. So what does that tell us about what we're adding? We're adding a strong base, that's what causes it to go up. If we're adding another buffer, we're going to get all sorts of weird things happening in there. Because then you've got two weak acids, weak bases interacting with each other, and that's going to convolute things. So when we start shifting to the right on our curve, what we're doing is adding a strong base. React the crap out of it, see what happens. So we're only looking at one species. So that question mark is best labeled. I'll try and keep all the new stuff we're adding in color so it stands out, is NaOH, so our standard strong base. It could be any strong base, but NaOH is the most common one. Okay. So what does it mean to be at the equivalence point?
It means that you have to keep.
Okay, you want to try first because he's been trying.
Is that an equilibrium? Isn't like the base is going oh, I'm so sorry.
It's okay.
It's going
I don't know if mine's off either.
like it's an equilibrium. The base is going to acid, the acid is going to base, and so there isn't or the hydrogen.
No.
Okay, so the hydrogens, the free protons are being used at a rate that it's not changing the pH. So as it's going from the reaction is happening, the acid is not, the number of free protons
So
is
you're
increasing.
suggesting a buffer point, okay?
No,
And
very
so
poorly.
here's where we're gonna have to be careful. What happens to our pH at the buffer point?
It stays the same.
Take a look at your equivalence point. Is your pH staying constant around that point? If I add a little bit of base or remove a little bit of base, is it staying constant?
Closely. Well, that one isn't.
What is the slope of that line?
That one isn't, but that one looks like it is.
How about that one? If I add a little bit of base, what happens to the pH? I go from something that is, what is that, 9.27 to now a little bit of base and I'm all of a sudden 10.
Yeah, there. Gotcha.
Okay, did my pH change?
Yes.
Changed a lot. Okay, what happens somewhere else on the curve? Let's say here. What happens when I add a little bit of
Oh, it's
base?
not changing that much.
It doesn't change as much. So what you're referencing is your buffer point. That's not your equivalence point.
The other points.
Okay, that's going to be what's known as your half equivalence. Before we get to the half equivalence, we still need to nail down what the equivalence is. Okay, so you're right, and that your half equivalence is your buffer point. Okay, and so I'll kind of roughly tag those if I can do that correctly here. I think that one's right, and I think that one's right. Okay, but that's kind of getting ahead of ourselves because we now have that labeled as our half equivalence, but we still don't know what our equivalence point is. Okay, so we need to know what the equivalence point is. Okay, you want to try and jump in, Robin, or you want to pass the mic again?
I would say the equivalence point is something to do with the amount of hydrogens in relation to the base.
Yes.
What exactly? I don't know.
Okay, so good. It has to do with the amount of hydrogen. So now we're going to run into a question here because it's a diprotic acid. Where's that hydrogen coming from? And the amount of base added. Do you want to layer on top of that?
I think, I was pretty sure that the equivalence was where the conjugate base equals the acid, but that's not quite right.
That's actually going to be the half equivalence.
Half equivalence, okay.
Okay. So, and it's not an easy one. Very rarely do we ever actually look at the equivalence point. In most cases, what you're interpreting is the half equivalence, because you get a lot more information out of that, or a significant amount of information out of the half equivalence point. Okay.
Equivalence is the pKa, right?
Nope. That's the half equivalence again. So again, your half equivalence has a lot of information in it, but to get to the half equivalence, we have to know what the equivalence is. Okay.
So at the equivalence point, the base is it's used at, and so the acid is just producing more free hydrogen, and there's no OH to pull it at. There's no base to pull it at, so that's why the pH is increasing at that point
At our
until you add more base.
equivalence point, our moles of OH
Are done.
sort of,
Are used up. You need more of them.
sort of, but we can continue to add moles of OH. So at any point on this curve, your moles of OH are used up. Okay, because it is reacting.
Right.
Okay, so yes, the moles of OH are used up, but what else is used up?
Acid.
Okay, and this is where we're going to have to be careful. Which acid?
Oh.
Because remember, this is a diprotic acid.
Of the first
So if I react this with base, what do I end up with? I end up with HA minus. And if I continue to react it with base, I would end up with A minus 2.
So
Okay,
You don't have to come out with it.
the moles of base
we'll come back to that.
equal to the moles of acid from the first hydrogen being released, whatever it would say.
Okay. However many moles of H2A we started with. Okay. At the equivalence point, the moles of OH I've added are equal to the moles of H2A I started with. Okay, why? Because what's happening at the equivalence point? The pH spikes. There is no more acid to react with the base. So as soon as I add a little bit more base, what happens?
Oh, it goes more.
The pH spikes. It goes up. It becomes more basic very, very quickly. Okay? That's why you're seeing that steep curve there. So that's what's happening with our moles of OH. Okay? This curve becomes trickier because how many equivalence points are there? There's 2. So we have to be a little bit more careful in our referencing with these. Our first equivalent is the moles of OH will be equal to the moles of H2A. What's true at our second equivalence point?
The moles of OH are equivalent to the moles of A or HJ.
Okay. And that one's actually got a couple extra things kind of odd going on with it. Where did the HA minus come from?
From the first.
From H2A. So at our second equivalence point, the moles of OH will equal the moles of HA minus, which officially really was our moles of H2A to begin with. Okay? But at this point, since we're in a new section of our curve, a second titration, if you will, or a second acid, what we're evaluating is now between point 1 and point 2, or point 1 in the end of our curve. Okay? Kind of, sort of. It's tricky. Okay. The only reason we would really use the equivalence point is if we were trying to figure out the molecular weight of our acid. So most people do a 152 lab where you're trying to determine the molecular weight of an unknown acid. Okay? And you do that because you get to the equivalence point. Well, if you know the concentration of NaOH, you know the moles of NaOH you've added to that point, which then means you know the moles of your acid. Well, you started the whole experiment off by weighing out the acid. So you know the mass of acid and you know the moles of acid. How do you figure out the molecular weight? The mass over the moles. Done. You've got your calculation. Okay. While the molecular weight can be useful, and we could potentially do that or use that information in biochem, we're a little bit more concerned at this point about the structural changes that go along with our acid-base reactions. We're concerned about our buffer position. Our buffer position is our half equivalence point. Okay, and this is where this one gets interesting. Let's take a look at the first one, because this will be our easiest one to look at. Let's say I start with 2 molecules of H2A. Okay, that means I have none of my HA minus. This is where we started. Okay, it's all H2A. Okay, I add a single equivalent of base. Okay, so this is my initial. Okay, base addition number 1. What does the base do to the H2A?
It abstracts the hydrogen.
It abstracts the hydrogen. So do I have H2A anymore? Once I've added 1 equivalent, I've lost 1 equivalent of the H2A. So how many H2As would I have left over? 1. Did I just destroy H2A and it's now disappeared? No, what does it become? What happens when you remove a single hydrogen from H2A? It becomes HA minus. So after a single addition of base, I have 1 HA minus and 1 H2A. Okay. I then continue to add base. So we'll say base addition 2. What happens to the H2A? I've added another equivalent of the base. We'd have 2 HA minus, but where did that second HA minus come from?
H2A.
The H2A. So how much H2A do I have?
0.
0. Okay. So at this point, the moles of H2A were equal to the moles of base that I added. That's how I come out at this 0, this net equals. That's my equivalence point. Okay, that's what we just addressed. Okay. The numbers I picked weren't completely arbitrary. I wanted a short example through it. And then also, I wanted a number that was big enough that we could then look at what happens halfway there. So if I have 2 equivalents of base, what's the half equivalent of base being added?
The first one?
The 1 equivalent of base. So after I've added 1 equivalent of base, I will by definition be at the half equivalence point, because I'm halfway to being at the equivalent point. What was true at the half equivalence point? So now I'm at the half equivalence. I know that's illegible. Okay. So, as Leanna pointed out earlier, at our half equivalence point, we are at our buffer, okay, or in our buffer range. Okay, and we could even say it's our ideal buffer range. Okay, well, that's too generic. I want a little bit more information. What else do we know to be true at that exact half equivalence point? Let's go back up to our drawing, looking at the individual reaction. What is true at the half equivalence point? So if we now erase all that other information, because we don't care about that now.
There's H2A and H2A minus.
Getting a little too numerical.
They're equal.
Yes. Okay. At the half equivalence point, what is true? The concentration of my H2A equals the concentration of my HA. Well, why is that relevant to me? Well, as Mike was suggesting earlier, somewhere on this curve we can figure out some information about the pKa of the acid. Well, how do we interpret pKa? Okay, we could go through all those fun, nasty ice tables, or we could use Henderson-Hasselbalch equation. If I want to solve for the pKa, I want to know the pH. On a titration curve, my y-axis is the pH. So cool, I know the pH. And I also need to know something about the concentration of my conjugate base with respect to the acid. Well, at the half equivalence, do I know something about the concentration of those?
They're equal, so that cancels out. So
I know the
pH
concentration of my acid is equal to the concentration of my conjugate base at the half equivalence. I don't care what the value is, but because they're the same, any number divided by that same number is 1. The log of 1 is 0.
So
What does that mean?
pH is pKa.
The pH equals the pKa at that point. Okay? All sorts of information just dumped right there on you. Okay? Is it quite as simple as that? I know that wasn't simple, but okay. Can we say that's the end of it? Well, how many half equivalence points are there?
3.
Okay, and this is where we run into some weird area. Why do you say 3?
It keeps going, doesn't
You
it?
see a flat line, you see a flat line, and you're seeing a third flat line at the top. There's a reason I didn't label that third one. We've reached the saturation limit. Look at our pH. We're at the max scale on our pH. We're actually reaching the flat line for water's ability to solubilize hydroxide. There isn't a buffer there. Water just can't hold any more hydroxide. Our acid isn't doing anything at that point. Okay? So we have 2 equivalence points, which then means if we go back and look at this, for our first equivalence point, these 2 statements are true. Let's call it A. But what happens when I get to the second equivalence point? What are now our true statements? We're in another ideal buffer range, but I don't want to rewrite that. What do I know about the concentrations?
The concentration of HA minus is equal to A2, or A minus.
Is equal to the concentration of A minus 2, which then tells us that the pH will be equal to the pKa. We have another issue popping up. How many pKa's? Okay, in the labeling system we've come up with, I only see pKa show up once, but at different pHs. Can that possibly be referring to the same acidic hydrogen? No, and we know that because we're looking at where we got that information from. It's a different acid-base reaction. So we need to clarify here. This isn't just pKa and pKa, it's pKa number 1 and pKa number 2. Well, which one's 1, which one's 2? Okay, why is pKa 1 our A answer and pKa 2 is our B answer? But I could have said B and A. It is completely arbitrary. We define our pKa as the lower acidity one. So if you've got 5 pKa's, so 5 acidic or atoms or locations on a molecule, you would have 5 pKa's. pKa 1 would be the most acidic. pKa 5 would be careful. pKa 5 has nothing to do with basicity because it's pKa. The A stands for acid. So it's not that it's more basic, it's that it's less acidic. Okay, and we talked about this a little bit before too. We have to be careful. pKa just tells us something about the acid strength. It tells us nothing about the base strength. Okay?
So you'd use
Or at
the
least
most
directly.
acidic one.
Well, it depends what you're looking at. Right? It's going to depend at the pH range. For instance, if I'm looking at a pH of 6.5, does it make sense to look at pKa 1? Why not? If I'm at 6.5, I'm somewhere up on this part of the curve. Does pKa 1 have any influence at this part of the curve? pKa 1's down here at a lower pH. Okay. So you have to choose which pKa to evaluate depending on the conditions you're set at. In a biological system, our physiological pH is pH 7, okay? 7.4. Which of these two pKa's is probably most relevant to look at for our biological systems? pKa 2 or B, okay? Because that's closer to our pH range. Kind of makes sense? Okay. So it is definitely not linear. You can't just say, oh, well, 1's the first one, so that's the one I'm going to look at. Or 5 is the last one, so that's the one I'm going to look at. You have to look at your conditions that you're at and say, okay, which one is most relevant to those conditions? This is different from organic or general chemistry, because in organic or general chemistry, we let the molecule dictate what we were going to do. You're not letting the molecule dictate now. You're letting the conditions dictate what happens. Okay. So we've marked probably the biggest pieces of information in here. Okay. But I want you to take this a step further. And there's a reason I'm going through and changing the color of our reaction. In the course of this titration, we move from H2A to A minus 2. So I want you to be able to point to locations on this curve and say, at this point, it is all H2A. At this point, it is all HA. At this point, it is all A minus 2. Okay. You got any ideas where you could point to nail those down? Where are you going to start? And if you're writing in pen, you might want to hold off. Let's walk through it first.
We can just use your rule of when the pH is less than pKa, then it's going to be in this format. When it's greater than this pH, whatever. And just go along the line and do that.
That gets you the bulk changes. Okay? The overwhelming majority of the molecule.
Right.
That doesn't say all of the molecule. What I'm saying is all of the molecules are in this form. Okay? So there's two easy ones, relatively easy to nail down. The beginning and the end.
Right.
Okay? I'm going to argue the end is probably the easiest.
Yeah.
Okay? Out here, it is all A minus 2. How about here? It is still A minus 2. Okay, so we could go through and label all of that, but let's label it where it first becomes all A minus 2. Where does it become all A minus 2? Where would I stop labeling A minus 2?
At the second equivalence point.
At the second equivalence point. At that point, it is now all A minus 2. because that's what happened when we got to our, whoops, where did it go? Okay. At that point, the moles of OH minus equaled our moles of HA that were added, which is now officially now all converted to A minus 2. That happened at that point. Okay. So how about the others?
So then the other equivalency point would be where all is HA minus.
The other equivalence point is now all HA minus,
But only at that point.
but only at that point. What happens if I slide just a hair down?
Then you have some H2A.
Now I have some H2A. Okay. HA minus is going to be in there on a much larger concentration. Okay, so we could say the overall charge in the solution is, for the most part, negative. Okay, but not every single molecule is negative. What happens if I slide up the curve ever so slightly?
You have some 8 minus 2.
I have some A minus 2 coming into it. Okay, kind of makes sense?
So then where's the H2A?
Now where's H2A?
Is it only at the very beginning?
At our very, very beginning, we have H2A. Okay. As soon as I move one step further up by adding base, what happens? I now have some HA minus. So it's not all H2A. Okay. Kind of makes sense? If you take a look at the practice exams, you have pretty much this blank graph, and I ask you to label the crap out of it. Okay? Because it is very important to be able to approach the graphical data and interpret. Very rarely are you ever told, here are some numbers, do a calculation. Okay? You're given a bunch of data, you have to determine those numbers, then you do the calculation. Okay? I'm going to leave the calculation aspect to future classes, if you so need it. Okay? Or to past classes, say 152, if you needed it. Okay? More than likely, what you're going to be more responsible for, or better at understanding, is the graphical data. How do you interpret to get numbers? Once you have numbers, it's then just a question of running through all those calculations. Questions about what's up here? I'm like serious here, because if I delete all this and you ask a question about it, I'm going to get kind of upset.
Looking at your sketch.
Okay, so let's wipe all that.
Oh, wait. No, I'm just kidding.
Okay. What if I gave this to you? It's becoming more acidic, so what am I adding? I'm adding an acid to it. Okay, so what did I start with?
Base.
A strong base. What happens at the first equivalence point? Whoops. There's my first equivalence point. What would I have?
You have the first part of the whatever is the opposite of the other one, the H2A.
We'd have HB plus. Because it's acting as a base, all we're doing is adding a hydrogen. What happens at the second equivalence point? Really shouldn't have done that part of it. I would have H2B plus 2 officially. Okay. Once you start to put on these labels of where things are, then it's a question of balancing out what you're looking at each of those stages. Okay. Kind of makes sense? This is a big curveball to throw at you. That could be a standardized test kind of thing. I don't think I'd throw this one at you because it's confusing enough as it is that I don't want to have to think my way through it. I'm happy with the acid one. Okay. Questions about that? Kind of get the ideas? Okay. So, if we were in the lab, okay, so this is part of it, we're trying to pick a buffer now for our reaction. Because what we're ultimately doing in biochem is taking everything out of the body or out of a cell and saying, do that outside the cell so that I can learn something about what you're doing in that big complex environment of the cell. Okay? But as soon as we take it out of the cell, what have we also removed? All the conditions of everything else that could have potentially been stabilizing and allowing the reaction to occur in the cell. So this is one of the things that made studying biochemistry initially very difficult. To say, oh, the cell does this really well. Well, I'm going to take that out and test it. And they put it in a container, and they say, well, now it doesn't work. So cells have something special in them allowing it to work. What's one of those things that's special? A buffer. That the pH remains constant, because as soon as we change the pH, it screws up the whole system. Okay? So depending on what we're looking at, we may want to pick a buffer to balance out our pH appropriately. So there's a variety of buffers to choose from. Okay, so I gave you a whole bunch. You'll notice you end up with these weird names for some of these: pipes, heps, tris. Okay, tris happens to be one of the more common ones. Heps shows up fairly often. Okay, why do they call them as these names as opposed to going out with the chemical name?
They're probably crazy huge.
They're crazy huge long names. Okay, so we came up with an abbreviation for them so that we don't have to refer to them by their actual full name. The other one, they're short enough that we can call them those. Okay. So what we would be able to do is then figure out some information about those, say by maybe even doing a titration curve. We now know the pKa's of each of those compounds. Okay. Those are now our buffer systems. I'm going to use those as my bulk buffer, and then I can test my reaction or my biochemical reaction in that buffer system. Okay. But is the pH the same everywhere in every single living system? No, it's different. So depending on what our pH range is or what our target study molecule is, we may want to choose a different buffer. For instance, tris, remember we buffer at the pKa pH range. So tris will buffer really well at 8.3 pH. Okay, and it's roughly plus or minus 1 pH range off of that before it's, that didn't make any sense. Ignore that. Okay. You'll buffer, no, that was right. You'll buffer about 0.5 either direction. After that, you've gone far enough outside of the realm of the buffer that it starts to spike, or it starts to spike upwards or downwards. So we're out of its buffer range. So tris will work fairly well as a buffer between, I can add better than I can subtract. So 7.8 to 8.8. Roughly its pH valid range. So given these pHs, what would be good buffers to use? So pH 1, what buffer is going to be your best bet?
Phosphoric acid.
We really only have one choice, okay? It's going to have to be A. Is that going to be a really good one?
No.
No. Okay, but it is the best option we've got. Okay, pH 4. Okay, this is a weird one. Where's the pH 4 fall?
In between.
Pretty much exactly between A and B. So it's kind of a hard decision to make. Not only is that a hard decision to make, but pH 4 falls outside of that plus or minus a half pH range either direction. So we're going to have a hard time buffering at a pH 4 with these to choose from. Okay. 6. Carbonic acid is probably going to be your best bet because it is closest to our pH 6. So we would probably do B. pH 7.
Hydrogen phosphate. D.
Also C too.
C and D are pretty darn close. They're plus or minus 0.2 either way. So both of those are actually pretty good choices.
Would
We'll call
you
these
then find
bad.
that you would rather use one that's more?
What you're starting to address is which buffer should we use given a choice. There's other things that factor into it. So our first whittle down is, does it match a valid range? We'll then say, are there other things that come into play? pH 8.
Tris.
Probably the last one, just tris. Okay. But if we put tris in and it's ideal buffer position where we have half of the protonated tris and half of the deprotonated tris, we'd be at pH 8.3. I want 8. How do I get this 8.3 to become 8? I add a strong acid to it. Okay? That strong acid will react with the basic form of tris, okay, reducing the concentration of the basic form of tris. What does that then do to the buffering capacity if more acid is generated in the reaction?
Limits it.
It limits it, because I've already forced it to shift off of the ideal buffer situation further down that curve, which means I have a much smaller section to play with before I start falling off the cliff. Okay? So to zero in on the exact pH we want, we'll add strong acids or strong bases to kind of nail that down perfectly. Okay? Just realize the larger shift that you're trying to make, the more or the less ability you're going to have to be able to buffer well, because you've now run out of that species to be able to buffer adding a strong acid or strong base. Does that make sense?
Can you add something that's not quite as strong to then, not have such a dramatic effect then?
Yes,
And that shouldn't that
but
increase the
then you potentially run into the issue of you're now adding, you picked a buffer, and you're saying the buffer's not good enough, so I'm going to add another buffer.
buffering?
So you're buffering a buffer, which would work,
Yeah.
but you've now increased the complexity of the system, and you may run into issues with things fighting each other.
I see.
Okay? Which comes down to our choices. Okay? Carbonic acid is going to be the best one to look at. I know our example was bad up there, but let's say we were aiming for a pH of, actually no, we could do it with pH 6. Okay? So in our choices here, we really only had carbonic acid as our best choice. Okay? Carbonic acid is H2CO3. If I want to study a molecule or an enzyme that works in our bloodstream, okay, would carbonic acid potentially be a good buffer system to use? Let's still say we're at that ideal pH. That's a pH roughly in our bloodstream sitting at 6. Okay, we have to make some approximations there. Is carbonic acid a good choice?
Yeah.
What is going through our bloodstream at the same time?
Carbon dioxide.
What happens when carbon dioxide reacts with water?
It's carbonic acid.
It forms carbonic acid. So as we are studying the enzyme, something else is happening to change the concentration of our carbonic acid, which then means what happens to the pH?
It's going to change.
We're going to get all sorts of weird things happening within it. Okay? So we want to make sure that the buffer we choose does not affect the thing we're studying. Okay? The buffer is there to just affect and level the pH. It should have no other contribution to the overall reaction. This is one of the reasons why we use these big complex buffers, because those buffers are complex enough that we're running under the assumption biological systems won't use them. If we pick something like carbonic acid, CO2 is already pumping through our bloodstream. It is in an equilibrium already with carbonic acid. We use carbonic acid naturally. If we use that as our testing solvent, okay, or our testing buffer, it can potentially interact with the systems we're studying. Now we don't know if the changes we're seeing are due to us playing with the system
Just happening on its own.
or just happening on its own. So we have to be careful with the buffer that we choose. Okay, so it's not just, oh, pH is perfect, pH and pKa are perfect, but what else could that enzyme or that buffer potentially do in our system? Okay. So in our buffer considerations, suitable pKa matching our pH, super, super important. Okay, that's our big one. Okay, no interference with the process being monitored. Okay, CO2 could inhibit the enzyme we're looking at. So if I pick carbonic acid as my buffer system, it generates CO2. That CO2 can mess with what I'm looking at. I don't know if it's me messing with it or if it's my buffer messing with it. Okay? The ionic strength, we already kind of vaguely talked about this one. If I pick a buffer where I take one molecule of the acid form, one molecule of the base form, that is going to put me at the perfect buffer system. Right? I'm at the ideal range. I add one molecule of acid, pH doesn't change. I add 2 molecules of acid, what happens? pH is going to drop significantly. There's no more base of my buffer left to take out that extra acid. So what we're referencing in the ionic strength is really a concentration. How much buffer is present? Okay? If I don't have enough concentration of the buffer, as soon as I add acid or base, I'm going to remove one of them and I no longer have the buffer. So I need to have enough concentration of them, the buffer or the pH doesn't change over a fairly large change in acid or base concentrations. Okay? That said, we could say, well, then I'm just going to completely saturate the solution with my buffer. Then I've got tons of buffer in there. As soon as I've saturated the solution, now what happens? What happens to water's ability to dissolve other things if water is already saturated with the buffer? It shuts down and doesn't dissolve anything else. So we have to include some solubility issues in our discussion or our thought process on that choice. We have to make sure that we can still dissolve everything else. Okay? Number 4 is kind of a tie back to number 2. Okay? Number 2 is more generic. If we're using any kind of system, maybe our buffer system is super reactive and actually changes the structure. Number 4 is a non-biological nature, okay? Meaning carbonic acid is a biological buffer. We want to avoid that because that's already constantly being used, and if we're changing, or if we don't change that, our buffer could be affecting what we're looking at. So we shift to a non-biological nature of the buffer in the hopes that it doesn't affect the system. Okay? Which gets us back to number 2, what if our buffer actually reacts with it? Okay? That's where we're kind of running in that system. We have to be kind of dicey and choose carefully within those. That's why we have a lot of those kind of new buffers, the pipes, the HEPs, the trips, all of those fun things. Tris, not trips. Okay? Kind of makes sense. So, just because I always got to do this, which of these would be the best compound to buffer at a pH of 10? Okay. So of course the next question would be, why? Okay. So the easy way to do this would have been what? How did we decide which buffer to achieve those pHs?
With the pKas.
We looked at the pKa's. Okay? So if we're now going to go through in this system, the easiest way to do it would be look up the pKa's for each of these. I'm being a jerk. No pKa's.
Jerk.
Okay? So without that pKa information, you're going to have to predict something about the reactivity of these species, which would then mean trying to decide where your difference in chemistry lies. We have an acidic hydrogen out here that could potentially work out. That's the same in both cases, and the pKa of that, of just those 2 positions. So number 1, those 2 are very, very close. What would that pKa roughly be? And if you got an idea on a different molecule, so you don't know the pKa, but you know a different molecule that would probably match that, that's fine. That looks an awful lot like sulfuric acid. The acidity at that position is very, very, very acidic, okay, which would suggest your pKa for those positions is somewhere in the 2 range. So neither of those 2 positions are our active buffer site. Okay. So now we run into the next dilemma on this. Okay. Where's the next most acidic position? But that nitrogen didn't have any hydrogens.
Well, on the first one.
So the first one does have a hydrogen. Is that hydrogen particularly acidic? No, unfortunately not. So this is one of the things that becomes tricky. When we draw out the organic molecules, we tend to draw them in their neutral state, irrespective of the pH. Okay. So bring pH. The pH is your controlling factor in here. Bring pH into this. Let's pick something that's stupidly acidic. If we're in the stupidly acidic pH range, what would happen to the hydrogen at the end? It should stay on because it's really, really acidic. If we're in a stupidly acidic environment, what would happen to the nitrogens? They gain the hydrogen. There's your acidic hydrogen that you're evaluating for the pH, or for this question. What you are trying to determine is the pKa, or the relative pKa, of that hydrogen. How do you decide that? That comes back to looking at acids and base strengths, looking at the environments and what things are different between these. Okay. I've already noticed in past semesters that nobody wants to go through and think through all of this. So I'll challenge you to try and spend some time on your own and come up with and predict these. But I'll tell you that the pKa's out of the gate, and if you've got questions about it, you can always ask me later, are 9.3 and 7.2. So given those pKa's, we would now say which one's our better buffer. Our first one, because it's closest to the pH of 10. Okay. Theoretically, based on your organic understanding, you should be able to tell me that this hydrogen in our second molecule is more acidic than in the first molecule. Because it is more acidic, what does that mean about its pH or its pKa? It's going to be lower. So given the choice to get a pH of 10, I want the one that is closest to 10, so not the lowest one, because a pH of 10 is pretty high. Okay. It does involve a sequence of kind of educated guesses and approximations, but that's kind of what we would go through and look at. Okay. Questions on that? Okay. So, blood buffering. This is one of the buffers used in blood. We take CO2, react it with water, we form H plus and HCO3 minus. So the buffering molecules, whoops, that's not our buffering system. Our buffering system is HCO3 minus going to H2CO3. Okay. Actually, that first one can buffer. It's kind of a lie. Yeah, well, let's just say that. Our buffering system is looking at the balance of these two species. Okay. So, this reaction is aided by a super efficient enzyme, carbonic anhydrase, that helps kind of balance, okay, between those two. So this means if we become an extremely acidic environment, what happens? HCO3 minus reacts with the H plus, turns it into CO2, and we can stabilize our pH by then having removed the H plus, so we stay relatively constant. Okay. If for some reason our pH becomes very, very basic, what happens? The H plus generated in this reacts with the base, we shift and we absorb more CO2, and we end up producing HCO3 minus. So that our H plus concentration, again, stays relatively constant. Okay, so it can buffer both directions. So as an interesting thought, what might we predict for the pH in our lungs or in our muscles? Okay. And realize there's a big here, because this may be counter to what you already know. Okay. If we're in an extremely acidic environment, what do we want to have happen? That means there's an excess of H+. We need to make CO2, okay, so that we can level out the pH. Okay. Well, where might we want CO2 gas? In our lungs. So we might predict, based on this reaction, that the pH in our lungs is acidic. So that when our blood comes up to our lungs, it's now very acidic, and what happens? The acidity forces CO2 out of our bloodstream into the lungs, and we can then expel it. Okay. What do we want to have happen in our muscles? Well, our muscles, we need to get the CO2 to our lungs so it could be expelled, so we might expect the opposite. Is that true?
No, it's off backwards.
Interesting. It's backwards. Okay. So if you didn't know that already, think about when you work out. When you work out, what do you end up feeling? You went running for a really long time. You feel fatigue. What happens to your muscles? They start to burn because lactic acid. Your muscles are becoming very, very acidic. Well, if they're acidic, what ends up happening? They would release CO2. We'd have gas in our blood system or in our vessels. When that got to your heart stops because it chokes on the air passing through it. That's a bit of a problem. Okay? So something odd is happening here. Is this the only thing buffering in our blood?
No.
No. There are other buffer systems, particularly a system that transports gaseous molecules known as hemoglobin. Hemoglobin is also acting as a buffer in concert with this. We have a buffer within a buffer. Okay? They are interacting with each other. And we'll talk about that when we actually start to get into our protein structure. Okay? Questions about that? Okay. So, as a general thought, is in an experiment to evaluate carbonic anhydrase, would carbonic acid be a good choice for a buffer? So carbonic acid was H2CO3, which is in balance with HCO3 minus. So is using H2CO3 a good choice as a buffer?
No.
No, it'll react as a substrate with our carbonic anhydrase. We're now seeing an odd dichotomy. Is the buffer actually causing the enzyme to do its job? Or is the buffer just sitting there and doing its own natural state? Okay. The buffer should only be used to balance H+. If it can interact with our enzyme, that is a horrible choice. Make sense? Tell you yes? I'm going to say it's a yes. Okay. So, can't quite ignore it. So if we had 100 milliliters of a 0.1 molar tris buffer at pH 8.3, okay, and I'll even tell you that the pKa is 8.3, and we add 3 milliliters of a 1 molar HCl solution, then what's our new pH? I forget. How many people had 152 recently-ish? Recently-ish? Okay, so you guys should be able to walk us through this, right?
Easy.
Remember what you have to do?
Not an issue.
Just pull it out.
What's that? Okay, we will need an ice chart or ice box,
Need an equation.
but we also need an equation. Okay, the ice chart only works for our weak acid, weak bases. HCl is a strong acid. So what we would have to do is first predict or determine the amounts of moles of our acidic buffer and our conjugate base, react it with the strong acid, which is going to change those concentrations, and then we can take those concentrations into the ice chart. Which sounds like a lot of fun, and I don't want to do it. So unless there's objections, I would say we don't worry about that. Okay. Good. Chapter 3. Okay. So when we move into chapter 3, it's now amino acids, and they're looking at kind of the basic building blocks. How do we work our way up through all the different, getting up to proteins? and they start to introduce the concept of what proteins are. Chapter 4 then starts to take it a step further. We start to look a little bit more at their function and how they are processed and put together. Okay? So amino acids, what are our building blocks? What traits do they have behind them? Okay, so is that a question?
Just a quick question, I guess. So are we essentially never really going to need to worry about like calculating anything in this class for the most part?
Okay, that last part of your statement is the true one, yes. In this class, we aren't going to worry about doing calculations like this. No.
Okay.
Maybe I'll throw it in there as it's a bit mean to throw it in as an extra credit, because then people that have had it could theoretically do it, and nobody else could, so that's not really fair. So yeah, I'm going to leave it out. The only reason I address it is that I know I have some other students that are potentially watching this that go to ASU, and I just gave them sort of a hint on where to start with that. And if they want to, they can come back to me and say, hey, how do you do that? Okay. So when we look at the amino acids, in chapter 3, what are the basics of our amino acids? What are they? How do they work? General pieces on them. So to start, amino means we have an amine group. So when we look at our amino acid, what do we immediately see? An amine group. Okay. You'll also notice that when we call it an amino acid, the amino starts first when we read it left to right. So when we typically draw out our amino acids, what's the very first thing we see? The amine group. Okay. That is a standard kind of notation. At least within the US, it should be everywhere, though not everywhere reads left to right. Okay, so theoretically, they don't swap it when they read different directions. Okay. The acid part in our amino acid is then the other end, and we have a carboxylic acid. Okay. So that's our basic piece within this. Okay. Our amino acids are monomers. Okay, they are the single unit. Okay, if we string together a bunch of monomers, we end up with a polymer, many repeating units. Okay. In biochem, we can't refer to it as a polymer because everybody flips out, so we end up calling it an entirely new thing, and we refer to it as a protein, or a polypeptide. Okay, and we'll come back to why we call it a polypeptide in a little bit as well. Okay. What else is kind of interesting on that slide, or something that you might note and start to dread? Okay, the R group is there. That's left nice and generic. Okay, so we'll talk about that. That's where we're going to get our variability within our amino acids. Comes back to that R group. What is that R group? Does that change the properties we see? What else might cause a little bit of a panic? pKa's. In our amino acid, we have pKa's. Why do we talk about all that acid-base junk? Because our amino acids are acids and bases. Okay? So they will react according to their pKa's. So you're going to be responsible for interpreting the pKa and the pH of where we're at and deciding what should the structure look like. Okay? What changes occur to the structure. Okay, so if I was at a pH of 1, what would I expect this amino acid to look like? pH 1, what do I got?
Everything's proteinated.
Everything needs to be in its protonated state. So if I look at my carboxylic acid, I need to have the hydrogen on it. If I look at the amine, I need to have my hydrogen on it. Where does it become a little bit tricky? The carboxylic acid already started in its protonated state. That one, when we look at it, seems to be relatively obvious. The hard one is recognizing what's happening with the amine. Okay? The amine is almost always drawn in the neutral state because in the neutral, or in that state, it's easier to draw. There's no charges. It looks prettier. Okay? That's the organic perspective. Remember, in biochem, it is now dependent on our conditions. So we have to make sure that we change the structure according to our conditions. You need to be a little bit more comfortable with
deciding what is the acidic form, what is the basic form, or the neutral form for each of these compounds. So we have to have the proton on both of these. What else is missing in the structure right now? As a hint, has to do with the nitrogen.
It's a positive charge.
It is now formally positive. Okay. Should the oxygen become charged? It has a hydrogen too. No, it has to do with how it was reacting to begin with. Okay. Why does this become important? Well, our charge changes. As the charge changes in the molecule, depending on the pH, we're going to get that molecule to respond differently. For instance, if I held up a giant negative wand, what's that molecule going to do with respect to the negative wand? It's going to be attracted to it, the negative to positive. So I can potentially separate this compound away from things that aren't charged or aren't positively charged by just holding up a negative wand. Okay? So magically, whoop, comes out. I've now purified it from all the other junk because it's positive. But if I had changed the pH to, say, a pH of 4, what happens when I wave my negative wand now? Well, so the first thing I have to do is adjust. Does my structure change at a pH of 4? Well, pH of 9 is, or pH of 4 is still lower than the pKa of 9, so my nitrogen should be positively charged. It should stay the same. What happens to the carboxylic acid? Okay. The pH of 4 is higher than the pKa, which means I need to remove the hydrogen as H+, which means the oxygen is now negative. When I hold up my negative wand, what happens? Okay. So we could see this weird kind of dichotomy of it swapping around. It doesn't swap around. We end up seeing the molecule as a whole. What is the overall charge on that molecule? Neutral. I hold up the negative wand. What happens? Nothing. So by changing the pH, I can change my ability to isolate the amino acids. Okay? So you need to be aware of the pKa's. You'll notice for the R group, I did not specify a pKa. Why not? That R group can be a lot of different things. Some cases it could have a pKa, some cases it might not. Regardless of what the R group is, for the most part, the pKa of the amine sits at 9. For the most part, regardless of what the R group is, the pKa of the acid sits at 2. Okay? So as long as you remember that those two are 9 and 2, now the only thing you have to really memorize when you look at your different amino acids is what is the pKa of the R group. Okay? I mean, I know we aren't there yet, but that's kind of your end goal on that. The next layer on top of this, we also don't really need to worry about the pKa of the amine or the acid. Why? What happens when I put these into a protein or a polymer? Is the pKa of the acid relevant? Nope, because it no longer has the OH, it's now connected in a bond. What about the pKa of the nitrogen in that next amino acid? Same deal, it's now connected in a bond. I don't care about its pKa anymore. So when we're looking at a protein, the only pKa's I'm concerned about is the pKa for the amine on the very first amino acid and the pKa for the acid on the very last amino acid. Then I care about the pKa's now on all those R groups running through the middle. At this stage, we haven't talked about the R groups again, but we're just trying to work our way through those steps. Okay. That bond, I'm going to kind of attempt to cover this up. The bond between amino acids is known as what? Okay, and as a hint, don't tell me peptide because that's going to annoy me.
Oh, you mean like a covalent bond?
No, that's not a bad idea. Functional group within organic chemistry. It's an amide. It's an amide bond. Why'd they call it a peptide? Because biochemists don't understand organic chemistry. Okay? They had to call it something different. Okay? They are one and the same idea. An amide and a peptide bond do the exact same thing. Okay? By calling it a peptide, now what can we refer to the polymer as? Instead of referring to it as a protein, we can refer to it as a polypeptide because it has many peptide bonds. Okay? This is something that I've noticed as a trend when it comes to naming things in biochem. They take something relatively simple, they name it something else, so that they can name it something else, so that they can come up with 6 different names to name the same thing. And you're responsible for knowing all of them. Okay? So just kind of be aware of those limitations when we go through and address these. We'll refer to proteins as polymers, we'll refer to them as polypeptides, we'll refer to them as proteins. Okay? We'll even refer to them as their name. What is the function? Carbonic anhydrase is a protein. Why do we call it carbonic anhydrase and not a polypeptide? Okay? For the same reason I don't call you just humans. Okay? We can get a little bit more specific. Make sense? Okay. Amino acids, and now the fun compound, or fun idea, stereochemistry. How many of you remember stereochemistry? How many of you loved stereochemistry? Okay. When we look at this molecule, okay, there's an interesting issue that pops up. The carbon that has the R group attached is known as a stereocenter, or a chiral atom, or a chiral carbon. Okay. Why? It has 4 different groups attached to it, or 4 distinguishable groups. Hydrogen, an R group, a nitrogen, and the carbon of a carboxylic acid. Okay. This becomes important because if we think back to the wedges and dashes, if I go through and now change, this structure and say that the R is now wedged, and if I look at the other possibility, say that the R is now dashed, are those compounds the same or different? Okay. There's a little bit of an obnoxious terminology swap there. They're definitely not the same. They technically aren't different. They are stereoisomers, yes, get more identified, and it is chiral. They are enantiomers. Okay. They are non-superimposable mirror images. Okay. Does this cause a problem when we go to look at our proteins? Potentially. Because if I change the orientation of that R group, I can drastically change the functionality. Thalidomide, somewhat infamous drug, is a chiral drug. It has 1 chiral atom in it. One form of the drug, thalidomide, cures morning sickness. So anybody that's gotten pregnant, really it just applies to women. Okay, be cool, thalidomide, I don't have to deal with morning sickness. The other form of thalidomide, when you swap it from either wedge to dash, is a mutagen, meaning that you no longer have morning sickness, but you give birth to a deformed baby. Trade-offs? Okay. And that's just a single chiral atom. Your proteins, you're looking at hundreds of thousands of amino acids. If each of those hundreds of thousands of amino acids has this slight variation, wedged or dashed, we can get massive variations in the chemical reactivity of those proteins. That is a massive, massive issue. Okay? So we have to come up with ways to identify the difference between those. Okay? This is where we would introduce what's known as the Fisher projection. Okay? And in a Fisher projection, what we do is change our viewpoint on that molecule. We take our highest priority atom, we put that up top, which is typically our carboxylic acid end. We take our lowest priority atom, which is typically our R group, and we orient those so that those bonds are aimed away from our viewpoint, both of them away from our viewpoint, okay, with respect to that carbon atom. If those two bonds are away, what does that necessarily mean happens to the hydrogen and the amine? They now must be aimed at you. So that if we look at our two possible orientations or two possible results, we would end up with these two images. And you'll notice that we do have that mirror image. Okay? If I dropped a mirror in between these, it reflects perfectly through. But there is no way I could superimpose. I can't take this molecule and overlay it perfectly on top of this one. Okay? As it's perfectly oriented, I could overlay the carboxylic acid in the R group, but then the hydrogen and the nitrogen aren't overlaid. If I do a rotation, I could potentially get the hydrogen and the nitrogen to overlay, but then the carbon and the R group aren't. Okay? So they are non-superimposable mirror images. That's your enantiomer. Why do we look at it in this formation? Okay. If you remember organic chemistry, we could go through and label it as R or S. Okay. In biochem, we decide to not use the terms R and S. We use the terms D and L. Okay. For somewhat reasonable reasons. So now the idea is what is, or how do we identify D and L? Number one, there is no connection to R and S. So don't use that. R and S is now out the window. You're dealing with D and L. So now the question is, what is D, what is L? Okay. As a hint, D is over here, L is over here. Notice as well, for those of you that may have seen it in organic, this is a capital D and a capital L, not lowercase d and lowercase l. Lowercase d and lowercase l refer to optical activity, which is how we would experimentally see that we have a chiral atom. We see how it rotates light, and we could refer to it as positive or negative, or lowercase d and positive or lowercase l. Okay. Again, not to be confused with R and S. Entirely different system. So what does the capital D and the capital L refer to? That's not quite the answer. The capital D stands for dextrorotatory. L stands for levorotatory. Anybody know your Greek or German or whatever that is? I'm not quite sure which it is. Dextro is the term for right. Levo is the term for left. When we are looking at our amino acid, or any compound for that matter, notice where our highest priority group is. We're comparing hydrogen to nitrogen. Which one has the higher priority? The nitrogen, which is located on the right-hand side of the structure, D form. If we look at our other amino acid, where's the nitrogen located? On the left-hand side of our drawing, which makes it the L form. That's how we differentiate the two. What if I took this structure and rotated it around so the R group was up at the top and the carboxylic acid would be down at the bottom? Where would the amine then show up? Careful. If I did a rotation along this, I would have COOH, I would have R. What would happen with my hydrogen and my amine?
Go to D.
It would be on the right-hand side. What's my name?
D.
What's my name?
Mike.
How about now?
D. Mike.
Still Mike. Okay. So it doesn't change. I'm going to just pretend I didn't hear the D part. Okay. It doesn't change. If we rotate the molecule, it had better not change forms.
Oh, because of the carboxylic. Okay.
Why? We're no longer looking at our structure in the way that allows us to assign L and D.
Okay.
We cannot assign L and D to my new drawing here because I'm not in the proper drawing orientation. Okay. To be in the proper orientation, you must have the highest priority at top, lowest priority at the bottom. And sorry, we're done. Okay. So yeah, the end on that was looking at our highest priorities. If you have questions about highest priority, talk to me after class. We'll go through and look at that and assigning R and S and getting roughly comfortable with it. It's going to come back again when we look at carbohydrates. Okay, a lot then. Okay, but that's our L and our D.